Hi, in this video I would like to explain how to solve a Bernoulli's equation problem in a very simple way. There is a bent pipe, the water flows through the inlet shown by those two arrows, and there are various cross sections indicated for the tube A, B and C, and we have to find out the pressures and velocities at the center point of these sections. The blue horizontal line here indicates the datum plane from which the height of the center point of the tube at each of these sections is mentioned. The water flow inlet conditions are mentioned. With that, we start to solve the problem. A quick look at the Bernoulli's equation. The energy per unit volume has to be conserved at every point along the streamline as the water flows through the tube. The pressure is an energy per unit volume, the rho g h is a potential energy per unit volume, and the half rho v squared term is a kinetic energy per unit volume. Write the Bernoulli's equation for inlet and for section A. You will have 3 terms on the left and 3 terms on the right. Put the correct subscript. For the left hand side, P inlet is 2.5 atmospheres is given in the problem, plus rho g into H inlet. H inlet is 3 meters from the datum plane, and plus half rho V inlet whole squared. We keep it like that for now. On the right hand side, we have PA atmospheres, which we have to find out, plus rho g into HA, that's 1 meter, plus the half rho VA whole squared. So there are 2 unknowns in this one equation. We have to find out VA in order to solve it. Apply the continuity equation, that's A inlet into V inlet must be equal to area at section A into velocity at section A. Now the areas at inlet and section A are equal because the radius is equal. Therefore, the velocity Vin must be equal to the velocity at section A. Therefore, since the velocities are same, if you look at the equation 1, the half rho v squared term will cancel out on both sides. So we can remove it, and the Bernoulli's equation will simplify to 2.5 atmospheres plus rho g into 3 equal to PA atmospheres plus rho g into 1. We now do the maths. We write PA atmospheres equal to 2.5 atmospheres plus rho g into 3 minus 1. Rho is the density, 1000 kg per meter cube for water. G is 9.81 meters per second squared. We will get PA is equal to 2.5 atmospheres plus 19,620 Newton per meter squared. So we have to convert either everything into atmospheres or everything into Newton per meter squared. In this problem, we have chosen to convert it into Newton per meter squared. So convert 2.5 atmospheres, and that becomes 253,250 Newton per meter squared. This we can add to 19,620 Newton per meter squared, and we will get a total of 272,870 Newton per meter squared. We can also convert it back into atmospheres as shown, and we will get 2.69 atmospheres. The conversion of Newton per meter square back to atmospheres is shown here as a further explanation. We now go to the section B, where anyway we have to find out the velocity VB. As usual, we apply the continuity equation. We can do that between inlet and section B or between A and B, it doesn't matter. The radius at section A is 5 centimeters, the radius at B is 3 centimeters, so the area should be smaller, therefore the velocity should be higher. Keeping that in mind, we find the velocity at section B, VB, as 4.17 meters per second, which makes sense, and do these cross checks in the middle of any solved problem. We write the Bernoulli's equation in full. between section A and section B. So all the three terms of the equation would apply because the heights are different between A and B, so potential energies are different. The velocities are different between A and B, so the kinetic energy would be different. So rearranging this, we will get PB equal to PA plus rho G HA plus half rho VA whole squared minus rho G HB plus half rho VB whole squared. Doing the maths slowly, we will get PB as 255,495 Newton per meter square. We can convert it back into atmospheres and we'll get 2.52 atmospheres. Does this make sense? It does, because the pressure is lower due to the constriction in the pipe due to the higher velocity. We now solve for section C. Here the trick is to make things simpler and to save time. We know that the radius of the pipe at A and C are the same. That will help us to get rid of the kinetic energy calculation. So we should not compare section B and C. We should rather do section A and C, just to save time. So therefore PA plus rho G HA is equal to PC plus rho G HC. We know HA is 1 meter, we know HC is 0.5 meter, we know rho, we know G. Putting that into the maths, we will get PC as 267,965 Newton per meter squared. We can also convert it back into atmospheres and we'll get 2.645 atmospheres. Now if you compile it into one box, you can see the pressures and velocities at the sections A, B and C, and this comparison will be a good learning to see why the pressures and velocities are behaving the way they are doing. Here's an animation just to visualize the flow. The fluid represented by those two arrows is flowing through the pipe, and the water should speed up as it enters that narrow section. It's doing that and exiting through the pipe. Welcome to subscribe to our channel. Do share it with your friends. Download the app, Physics Models, or log in to our website. I hope this was useful for you. Thanks and have a great day.